polyhedra, then there are these 5 Platonic polyhedra that are the most regular. Again, all of the vertices, faces, and edges are the same, and so they represent the simplest possible regular maps. The hallmark of a regular map is that you can not distinguish the edges or the faces or the vertices. In principle, you can take any one edge, like the orange edge here, move it to any other position, put it there in 2 possible orientations, and then the whole network needs to be able to fall back onto itself. So every vertex will find another vertex, every face will find another face, and the whole network comes back to coincidence. On genus 0, that means blob-like objects that do not have any handles or any tunnels. These are all the regular maps that exist. There are the 5 Platonic solids, but in addition, there also are the hosohedras and their duals, the dihedras. The hosohedras are composed out of 2 gons. They're essentially these orange slices. They're exactly 2 vertices, one at the North Pole, one at the South Pole, and then you have n possible edges connecting the 2 poles. The dual of that is simply composed out of 2 hemispheres and an linear n-gon, essentially separating the 2 halves. And again, you can see in those structures, we can take any edge and move it to any of the other edges, and the whole network will come back and fall back onto itself. There's nothing wrong with having curved edges. As a matter of fact, as we go to more complicated maps, we have to become more forgiving even about geometry and really focus on topology, that means the connectivity. To understand this, let's look at some regular tiling patterns. I've had a long-lasting fascination with geometrical tiling, and MC Escher is one of my heroes. With my students, we have generated not only patterns in 2D, in the plane, but also created a generator that allows to do such patterns on the sphere. And then later on, we created patterns on a torus. A little later, we even extended that and advanced to hyperbolic surfaces of higher genus. On the left, you can see a virtual model that packs 24 Newt tiles onto this genus 3 surface in the form of a tetrahedral frame. And on the right, there's actually a tangible physical model created on our fused deposition modeling machine. It is composed out of 48 tiles forming a genus 7 surface in the form of an octahedral frame. Now you may ask, in what respects are these tilings regular? Since surely not all the tiles are exactly the same. And indeed they are not. For the octahedral structure, there are 2 types of tiles. The larger outer tiles shown on the top half circle, and then the smaller inner tiles on the bottom. But they look somewhat the same. 6 different sets in different colors of these 8 tiles have been used for the full assembly. And here you see the assembly partially completed. So, what should we accept as proper tilings on highly curved surfaces of higher genus? In the plane and on the sphere, all tiles can be truly the same because they're identical in geometry and they can really be brought into coincidence. But on tori, or on these higher genus surfaces, we have to be more forgiving. We only ask that these tiles are topologically the same, and we accept that the tiles will be stretched on the outer parts of, say, the torus, and compressed on the inside. However, the connectivity of these tiles must be regular. That means all the tiles must have the same number of sides, P, and Q of them must always join at every vertex. If this is true, then we have a locally regular tiling. To obtain a truly regular map, we demand, in addition, that there's also some global symmetry. That is what I outlined before, that every flag in the map, and a flag is this combination of one vertex with one edge and a piece of a face, that all of these flags are indistinguishable. You can move any one of these vertex edge combinations to any other place and put it there, and then everything must fall back onto itself. To make this possible, we can assume that the whole surface is covered with, say, something like nylon stocking. And you draw your network with a felt tip marker. And then when you move things, you can stretch and compress things and adjust it. And as long as the topology is correct, the connectivity is right, then you can again match every vertex with another vertex, every edge with another edge, and so on. So let's look at this global property. If you assume that this torus is covered with this kind of nylon fabric, and we put this particular pattern on there, then indeed we have a regular map. But in this case, we do not have a regular map. Why not? Well, because the number of edges that go along the outer surface here is different from the number of edges that go around the small circle. That means if we were to take that whole network and we rotate it 90 degrees around the center of this green marked tile, then the network will clearly not come in coincidence with itself. As you can see here, here's a torus with 9 times 5 array of quad tiles on it, and here's the original state. Then if you rotate it 90 degrees, you can see these two networks will not line up. But if we keep the numbers in both directions the same, as on, say, an 8 by 8 quad tiles, then we can do this 90-degree rotation, and indeed we can fit the network back onto itself. So there are infinitely many regular tilings on the torus. Just take a square array of n times n squares, map it onto this nylon stocking, and that's a regular tiling. There are also tilings composed out of hexagons and of triangles that form regular tilings on a torus. Now, until about 1980, only a few regular maps of higher genus were known. Then Coxeter and other famous geometers started to look specifically for those kind of regular maps. And every time they found one, it was a big event. But for quite some time, it remained unclear exactly how many such regular maps might there be. Here are two well-known classical examples. The genus 2 map, called R2.1, on the left, has the same symmetry properties as the quaternion group. On the right is the famous Klein quartic with 24 heptagons embedded on this tetrahedral frame of genus 3. Now, let's look in more detail at these white tags and what these numbers mean. These expressions characterize a particular regular map. The leading capital R says this is a regular map. Then we read the genus of that map, and next we find a simple numerical identifier going from 1, 2, 3, 4, 5, for all the regular maps of a particular genus. If this is followed by a lowercase d, it means it's the dual map. In curly parentheses, we then find the Schlafly symbol P, Q, used to define a regular tessellation by the number of sides on each polygon and the valence of each vertex, how many of these polygons come together at that point. Finally, the Petri polygon, that last number, is a zigzag path on the edge structure of this map. You always go sharp left, sharp right, sharp left, sharp right. And this Petri polygon always gets back to itself at some point. If it's a regular map, it will always take exactly the same number of steps, no matter where you start and in what direction you start. If you find two different Petri polygons of different lengths, it means you do not have a regular map. And the beautiful sculptures here on the right that celebrates this particular geometrical structure. It's carved out of marble by Elam and Ferguson. And for this particular map, the Petri length is 8. So if you go along these edges, left, right, after exactly 8 moves, you'll end up on the same point. And so Elam and Ferguson calls this the 8-fold way. And of course, eightfold away means a lot to physicists, you know, the symmetry of the elementary particles and all of that was a big thing. It also goes further back, you know, to the ways of enlightenment and Buddhism. So it's a very clever sculpture with a lot of connotation to other domains. Now, in 2006, Marston Conder of the New Zealand Institute of Mathematics published a list of all possible regular maps from genus 2 all the way to genus 101. He found these by an extensive brute force computer search using concept of group theory and symmetry. And here's the beginning of his very long list. He found a total of 6,104 regular maps between genus 2 and genus 101. Each of these maps is described by 3 lines of text. On top, you find first that symbol which I just explained. It tells you how many symmetry operations, different symmetry operations there are that bring this thing back onto itself. And this one tells you whether 2 faces meet just once, or maybe they wrap around and meet 2 times or 3 times or more. Okay. And then the bottom string here basically describes the connectivity. These are so-called relators. Every one of these expressions is a sequence of transformations, and if you carry them out for the full string, you will bring that object back to itself in exactly the same position. More about that later. By the time he published this list, there were visualizations for less than about a dozen of these regular maps, because that's all you get from the mathematicians. Job done. Here's the list. What else is there to know? Well, I would like to see what they look like, right? But mathematicians, no. Famous computer scientist Dijkstra once stared me in the eye and says, "Pictures are the crutch of the weak mind that cannot see the concept without that help." All right, I took that. But I still want to see those pictures. By the fall of 2008, I'd become aware of Conder's list, and I noted that there were quite a few of these regular maps that had not been solved, had never been really visualized. For genus 2, there are 10 maps. For genus 3 and 4, there are 20 maps each. For genus 5, there are 26 maps, and then the numbers grow slowly with the genus all the way up to 101 and beyond. Now, I wanted to have a nice symmetrical rendition of these maps, and some of them were easy to figure out, like the 2 examples shown here are 2.2 and are 3.6. They all have quadrilateral faces, and they show a very clear pattern. You know, 2 of these quadrilaterals form one of the arms, and then these arms do come together, either in odd numbers at the pole or in even numbers over there. And that's a pattern that allows you to predict how things are going on. So there's a map R4.4 that fits that very same pattern. It has exactly the same kind of structure. It has 5 of these arms. And then there is a map R5.7 that follows exactly this pattern, except it has 6 arms rather than 4. So using these systematic kind of patterns helped me to find very quickly some of those maps. Actually, the first time that I struggled to find a nice symmetrical embedding of regular maps was in 2004. The challenge was to find a symmetrical placement of 12 valence 8 vertices on the surface of genus 3, and a nice solution that resulted from placing these vertices, one on the outside and one on the inside, on each one of the 6 tetrahedral edges of this particular frame. And the ensuing model that you see is shown here. In 2007, I started to explore regular tilings on these cube frames. So cube frames are basically of genus 5. And here is a nice example of a pattern on a cube frame, but it's not a regular map. It's just a locally regular tiling. Because if you were to go around these various butterflies and do this zigzag path, you will find that there are closing zigzag polygons of a different length. I later tried to find the true regular maps on these highly symmetrical genus 5 surfaces. With a lot of trial and error, I later found the solutions which I presented at the annual Bridges Art Math Conference in 2009 in Banff. Some of these mappings took me a couple of hours, some of them several days. Gradually, during 2009, I developed a somewhat systematic approach that often seemed to yield success. And here's a brief outline. Depict this map on a Poincare disk, look for likely symmetries, place all the vertices with the stubs of the emerging edges in some symmetrical locations, try to complete all of the interconnections, and then clean up and beautify the model. And I'm now going to show these steps in more detail. Here's step number 1. The first step is to make a Poincare disk which has the right kind of tessellation P, Q. And that's very easy, because you can find applets on the web, and you just type in P, Q here, and push the button, and you get these nice, beautiful drawings. The next step is a little bit more tricky, because now we need to cut out a finite domain of this Poincare disk, which has infinitely many facets. But the regular map is really finite. It has 24 heptagons on the Klein map or so. In order to figure out how much of this Poincare disk we need to make exactly one copy of this map, we use these relators that Cox describes. And these relators are described in the form lower or uppercase R or lower and uppercase S. R means rotation around the face center. Capital R is a counterclockwise orientation, lowercase r is a clockwise orientation. S are rotations around vertices. Again, capital S counterclockwise, lowercase s clockwise. So if you look for this particular relator on this map, we might start up here, and we first do a counterclockwise rotation around the center of this particular face, which brings us here. Then we do 2 clockwise orientation around this particular vertex. Okay? Then we do another rotation around this vertex, counterclockwise, which gets us here, followed by 2 more of these clockwise orientations around the vertex. And that then tells us that basically this arrow is the same as that arrow, this vertex is the same as that vertex, this edge is the same as that edge, and so on. Okay? So that's how we tediously establish exactly what points on the Poincare map are the same. And then we have to pick exactly one copy of each one of those. And typically, applying this just once is not good enough. You may want to apply this again in a different corner. We see the same procedure here. And typically, Marsden conjugates half a dozen or so of those relators. And you have to apply several of them until you really know what's connected to what. But eventually, we should be able to color the whole disk with unique colors and label every facet, every vertex, every edge with a unique identifier, so there's no doubt what's connected to what. This complicated labeling then gives an idea of what kinds of symmetry we might expect. For instance, in this case, there seems to be a clear threefold symmetry around every vertex, because the sequence of neighboring vertices repeats 3 times. For instance, around vertex A, we find the sequence B, C, D, E, B, C, D, E, B, C, D, E. Okay? So that then implies that if you want to make a regular model of that, maybe we should look for a handle body that has somewhere some threefold symmetry, where we can place that vertex A and then use the threefold symmetry to match up with the threefold symmetry in this connectivity. Now, there's no shortage of low-genus handle bodies. I made this particular chart way before I knew about regular maps and all that for an art exhibit about 25 years ago, just looking for really nice smooth shapes of genus 2, genus 3, genus 4, and genus 5. And you can see we can pick them with threefold symmetry around the vertex, fourfold symmetry around the holes, or with fivefold symmetry there and twofold symmetry around the holes. So we have this variation of picking a handle body that might work. Now comes the least well-defined part. And this one needs the most intuition and plain guesswork. Where should we now place the vertices and how should we connect them? For instance, for the regular map 5.10, which has 8 vertices of valence 6, and also 8 hexagons as its faces, it would be quite possible and plausible to pick a cube frame and then place the 8 vertices on the outside of the 8 corners of the cube. And because you also need to accommodate the dual of this map, it's fine because with this arrangement we could take the 8 face centers and put them sort of on the inside of the corners on the cube frame. That seems very logical, and of course I did that. And then I started looking at Petri polygons. I found, oops, there are some Petri polygons length 4, some length 6. This is not a regular map. Okay. Next I try to move half the vertices from the outside of the corners to the inside. So basically, 4 tetrahedral vertices would have the vertices on the outside, and the other 4 would have them on the inside. And again, I happily checked the Petri polygons, no cigar. Actually, the symmetry of the figure had to be reduced even further. And we had to reduce it all the way to that of an oriented tetrahedron. And the hexagon had to be stretched and twisted even more in order to obtain the proper solution for this map 5.10. Now all the Petri paths are of the same proper length, and that's length 4. On the left you see a virtual rendering with all 8 faces shown in different colors, so they really stand out, and you can see how far that yellow winds around. It goes from here in its center and has a tentacle there, another one there, another one down here, and each one of these faces is kind of doing the same crazy thing. And then on the right you see an actual paper model of that same map with just 2 colors, so I could actually make all parts the same and just copy it and glue it together. Okay, so by now you should understand what regular maps are. Now let me show you some nice symmetrical results, and only then will we tackle the issue of putting such regular maps on non-orientable surfaces, because these surfaces will have self-intersections and they will be much harder to visualize. Let me give some credit to Jack van Eyck. He used a computer-based method to find some regular maps. He starts with some simple regular handle body, like a tetrahedral frame of genus 3 or some torus. And then he places a regular edge pattern, and there are 3 possible edge patterns that he would use, so around each one of the arms of such a structure. And then he just let the computer check, counting these lengths of the Petri polygons, whether maybe that makes a regular map. So it's a brute force approach, just generate something and check. Most of the time, no cigar, but every now and then he actually gets a result. And here are 2 nice results. On the left, he basically started from a dodecahedron, tubified, all of the edges. And then he took, I think there was a 3rd pattern I showed you before, put that pattern around each of the faces, tries all possible twisting, okay, to connect up the edges nicely, and then he starts to ask the computer, check that, whether that's a regular map, whether that thing shows up in Con's list. And if it does, okay, success, and he puts it in a list of published results. Here is another one, and you can see the underlying geometry started from was a torus. And on that torus, we had a 3 by 3 array of tiles. So basically 3 around that way, but also 3 around that way. And we know a 3 by 3 array in a torus makes a regular map. Okay. So we start with that regular map. We take all the edges of the regular map, we make them into tubes, we take some kind of twisted edge pattern like that, put them on the tubes, connect them all up, ask the computer, is this another regular map? And the beauty of this is recursive. Once you found that this is a regular map or this is the regular map, you can continue and says, okay, now let's make the edge frame, all of the little black lines, and make them into little thin tubes. And each tube segment, you do the same thing. You put one of these crazy edge patterns on there, connect them all up, and then you ask the computer, do we have a chance? Okay, so here again is the outline. For any regular edge configuration that he finds, he essentially takes the wireframe, he fleshes it out into this thin tubular structure, and then this handle body can be subjected again to the same treatment. So it's a recursive approach that may yield an unlimited number of results and actually go to very high genus very quickly. But unfortunately, you cannot say, okay, I know there's a regular map or 4.2. Let your program give me the regular map for it. No, that's not how it works. It can generate these things, and every now and then it spits out a regular map. It may not find some very trivial one, and it may get less than optimal solution for some of the simple ones. On the other hand, I think that's the result he presented in his SIGGRAPH paper in 2010, I think it was. It was of genus 29, and it was obtained in one of these recursive, I think at the third level of recursion, you get this kind of structure. And indeed, the computer tells us this is indeed a regular map, and it turns out to be R29.1 in Cantor's list. So, altogether by 2010, Jack had found 50 or more of these symmetrical embeddings, but some simple maps like 2.4, 3.3, his program couldn't find. Also 7.1, which is kind of special, which I worked on for 3 years until I finally found the solution, his program couldn't find. And sometimes the results don't look all that good. For example, here is the map 3.8, and clearly his program does seem to do some unnecessary warping, and it has a big circle here and has smaller circles and all of that. But there exists a very nice solution on a genus 3 tetrahedral structure. And this one seems very straightforward and logical. Okay. And for the map 3.11, same story. Kind of, this looks kind of twisted and warped, but with the same basic topology, but without any asymmetrical warping, you can make a very nice pattern. We just need two vertices. One goes on the outside of the North Pole, the other one goes on the inside of the South Pole, and they look kind of, like flower leaves or flower petals. So I call these vertex flowers. Now the interesting thing is, once you see that, you wonder if instead of 4 arms, I only have 3 arms, or 5 arms, or 7 arms, or 20 arms. Would that make another regular map? And the answer is absolutely yes. And so in one fell swoop, you have a whole series of regular maps that essentially pop out. No computer, just basically a little bit of intuition. It even works down for the torus, where we know there are infinitely many regular maps, and one of them has exactly that pattern. One vertex on the outside North Pole, the other one inside South Pole, and then a green set of petals and an orange set of petals interleaving and connecting those two poles. And that pattern just exists all the way. So here are some of the models that I've generated over the years, and you can see the wide variety of different solutions, but also the wide variety of different approaches. Okay? Some of them are purely virtual. Okay? Some of them are actually built as paper models, like those two. There are other ones which I just built up at like 2-dimensional flat disks painted in front and back. And the virtual ones were, rather than using a finite object, I put the map on one of an atom in an infinite grid, okay? Because that also allows you to make this nice regular connectivity. Okay, now you really get to the new stuff in this talk. Because now we want to construct such models on non-orientable surfaces, such as Mobius bands, Klein bottles, and the like. Unfortunately, there exist no regular maps on the Klein bottle. And that's kind of strange and surprising, because Klein bottle is of genus 2. And remember, on the torus, we had infinitely many regular maps. And now comes the Klein bottle, and because of this inside-out twist, said, no regular maps, sorry. Okay. However, there are several regular maps on the simplest possible non-orientable surface, which is the projective plane. And let me get you familiar with the projective plane. The concept is very simple. We start with all the points on a sphere and project them from the center onto both sides of a plane. It's simply clear what happens here for the red points up here. We simply project them onto this plane. But then there are also the blue points. What should we do with those? Well, we sort of backward project them. And now every point on this plane basically gets a red dot and a blue dot. And so it's kind of a double coverage of this thing. Also, if you look at the red person, okay, as this red person walks off in this particular direction, and we look at the beams that go to that person, we're basically going through the horizon here shown in green, which is something at infinity. And then that person comes back out of infinity, but look where he's coming back from. He's coming back from over here. Okay? So you walk off in the northwest, you come back from southeast. Not only that, if you look at a ray to the head of the person, another ray to the foot of the person, basically the feet are ahead in a clockwise sense of the head ray. We need to maintain this kind of orientation as we go through infinity. And if we do that, we find out that, oh my gosh, this person got mirrored upside down. And so on the projective plane, as you send something through this infinity loop, it comes back from the other side and it's upside down. Actually, if we take the strip on which this person walks and cut that thin strip out of the projective plane, you get a Mobius band. Okay? All the points on the horizon here, they basically go off to infinity, but not a single point in infinity. It's an infinite set of infinity forming another line. So, the projective plane is really a marvelous thing, okay? First of all, it's single-sided. That means if you start flood filling somewhere and spreading paint, the paint will go off and through infinity, and before you know it, has also essentially painted the other side. Okay? It is non-orientable, as we've seen. You take a right-hand person, basically send him off to infinity, comes back from the other side, suddenly that person is a left-hand person. Okay? A straight line does not cut that plane apart. You draw a line, and you're stepping on one side. You can always go through infinity, get to the other side of the line. You never ever step over that line. Okay? So it's really cool. The only thing is, it's infinitely large, and that's kind of somewhat impractical. Wouldn't it be nice if you had a nice finite model that we could hold in our hands that have all the same topological properties as this projective plane? So let's try to make a model. And we do that by essentially assuming that our projective plane is really not infinite, but just a very, very large square. But we know, in principle, we have to connect opposite points, because if I'm walking off here, I'm going to come back here. So these 2 points must be the same, and these must be the same, and these must be the same, and so on all the way around. So can we make a model in 3D space that somehow folds up this square in such a way that opposite points will actually come together? Yes, that's how we do it. We start out by taking the square and essentially letting it droop out, inflating it in an ever bigger pouch until it's a giant, humongous balloon with a square opening. And now we need to bring these two opposite sides somehow together in red and the two green ones, and we essentially do this zigzag fold. So we have this square opening here, and we simply start to folding it up until all 4 of these arrows fall into one and the same double intersection line. Now the 2 reds come together as they should, and 2 greens come together, and the result is shown here, and it's known as a cross surface. I will later relate to a cross surface where we have cut off a little bit on the south pole, and that would then make a cross cap. So if this thing were closed back here, and you don't see that it's open, then that would be a model of the cross surface. And you can see how the surface essentially passes through this double intersection line out here. Red goes in, and then it comes essentially out the other side, having been twisted inside out. Okay? And then if you cut off the bottom of the pouch here, then it's no longer a cross surface. I will call it a cross cap. And that's going to be a very handy and nice building block. Okay? Because any surface you have, if it's not already single-sided non-orientable, you drill a hole, you put one of these things on there, and voila, you can cheaply go from one side to the other. The surface has become single-sided non-orientable. Okay? Very handy. Okay? Now, this is not the only model of the projective plane. So here again is the cross surface. Steiner, when he was in Rome, and so that's why it's called Steiner's Roman surface, came up with this particular structure. It sort of has this kind of crease, but actually it has 6 of those. Okay? But you buy tetrahedral symmetry. So if you like a lot of symmetry, Steiner's Roman surface is as good as it gets. Gives you full tetrahedral symmetry. But you get 6 of these pinch points, which are called with this umbrella. Okay? Now, mathematicians didn't like those points because at this point, surface curvature goes to infinity. They would like to have a nice smooth model. And they didn't know whether it's possible to make such a nice smooth model until in 1901, Werner Boy, a student of famous mathematician Hilbert, actually found a way to do it. And he came up with this particular surface which has nice threefold rotational symmetry, and it's named after him. It's called Boy's surface. And again, with Boy's surface, which you kind of see here, if we cut off the South Pole, you get this kind of cup or cap. And I call this a Boy cap. Same as the cross cap, it's a thing that you can plunk down on the surface after you cut out the circular hole and turn that surface into a non-orientable single-sided surface if it isn't already one of those. Okay, so it's very handy to have these little caps, just prop them on a surface. I'm going to use those building blocks to make surfaces of arbitrary genus. Because it turns out you start with a sphere which is genus 0. Every time you plug on one of these, the genus goes up by 1, so you can get any surface of any genus you want. Okay, now the question is, are there any regular maps on the projective plane? For the 4 Platonic solids, for 4 of the Platonic solids, yes, there exist regular maps, and they're shown below their essentially father. Okay? In each case, we take sort of half of one of the Platonic solids, we cut it apart along a zigzag line that roughly approximates the equator. So we have this up-down zigzag path for the cube. The hemicube only has 3 faces. Okay? And now comes a trick. We essentially define that opposite vertices are the same. So we do the same trick as we did with this square frame. We connect opposite points, and that of course makes this into a projective plane. And in each case, for each diagram, you can see that happens. The hemioctahedron has only 4 triangles, okay, and only 3 vertices. And in both cases, we lose essentially half the faces and half the vertices. And every time the perimeter has to be connected, so in opposite points matching up and arrows flipping over. Okay, this now, we start looking at the hemioctahedron because it's a really simple case. Okay. This shows how we can deform this into a Steiner model of the projective plane. Each of the 4 triangles that we have in this regular map gets closed into this triangle pouch. So we take this triangle face and we kind of close it up as shown here and make it into one of these pouches. And then 4 pouches, colored differently, are put together. And so you can see these double edges, they do not really connect to one another, they come together at 90 degrees. But they connect with the double edge of another pouch, and that essentially makes a crease where 2 surfaces pass through one another without knowing of each other. Right? You're not allowed to step around 90-degree corner, you're only allowed to pass straight through. That is Steiner's Roman surface in a simplified polyhedral model. And so there's a direct mapping of this hemioctahedron into the structure you see on the right. Next, we can also map the hemicube onto the Steiner surface. It's a little bit more complicated. The hemicube has only 3 faces, but it has 4 vertices. So these vertices are naturally placed on top of the 4 tetrahedral bulges of the Steiner surface. And then the 3 facets essentially intersect one another in the 3 axes of an ordinary coordinate system. I'm showing 4 quadrilateral faces here. I show an edge pattern that allows you to actually slot them together so they have 3 mutually intersecting squares around the origin. And then for each square, you basically bend 2 of its corners up and the other 2 corners bend them down. And 3 of these corners being bent together then form one of these pouches on the Steiner surface. And so the result is shown on the right. That is a map of the hemicube, also mapped onto the Steiner surface and therefore has full tetrahedral symmetry. Now, for the hemiicosahedron, we can use the same basic decomposition of the Steiner surface into 4 quadrilateral domains. I'm not showing the slots here. Okay. Then we have to partition each such quad into 6 domains as shown, representing 2 complete triangular faces, C and D, and 1/3 each of the other triangular faces, A, B, E, and F. And together with the corners of the other 2 quadrilaterals that we're putting together, they then form the bulges on the Steiner surface. And by partitioning the 3 quadrilaterals of the hemicube faces in a different manner as shown here, we can also accommodate the hemidodecahedron on the Steiner surface. Each of the 3 quadrilaterals now carries parts of 4 different pentagonal faces. In 2 of them it has like 2 edges of the pentagon, and for 2 other ones it has 3 edges of these pentagonal faces. And the result is shown on the right, but I think you'll enjoy it if I show a short movie how this thing rotates around, so hopefully this now works. So here is that particular object. So that's the hemidodecahedron mapped onto the Steiner surface, basically using the same decomposition used for the hemicube, just essentially putting the partitioning lines in different places. And you can see this is still a tetrahedral shape, but there's kind of a twist to it. So it's no longer the full mirror symmetric tetrahedral symmetry, it's only the oriented tetrahedral symmetry. All right. Okay. Business here. Now at this point I would like to give credit to Conrad Poultier, who has done a very nice embedding of the Peterson graph on a crosscap. Turns out that the Peterson graph and the hemidodecahedron are pretty much the same. Here's my diagram of the hemidodecahedron, which you kind of understand. It's just the top half dodecahedron cut apart at the equator. But now, if we kind of take vertex 7 and force it over here, match it onto 7, and 6, the one with just 2 edges, force it over there and connect it, you get this self-intersecting, crossing kind of thing. That's known as the Peterson graph. And his group and his students made this beautiful semi-transparent drawing of taking this graph, which can be embedded in the projective plane, and they put it onto the crosscap. So they put the base or cross surface, they actually put it on this object. Very beautiful, but it does not have quite as much symmetry as the solution that I showed you, which has tetrahedral symmetry. Now, there are also the hemihosahedra and the hemidihedra, and for both maps I would like to use the crosscap now. The single vertex of the hemihosahedron goes onto the south pole, down here. And then these orange slices that we have for all of the, what originally used to be a 2-gon, okay? Now by cutting it apart, essentially it becomes a 1-gon. It just goes kind of from that vertex up and over and so back to that vertex again. Okay? And you can see a solution here with 12 different colors. So that's a hemihosahedron with 12 such slices. And n equals 2 is particularly interesting because it's kind of self-dual. Okay? So it's the hemihosahedron as well as the hemidihedron, which just has a single loop with 1 vertex on it. That's about as simple as it gets. And then there are also possibilities of getting more symmetry. Because let's face it, this one basically has just 2-fold rotational symmetry. If you only look at the shape, it has a sort of mirror symmetry. But could we have more? I mean, if we have like 60 slices or something like that, n equals 60, it would be bad to only have to live with just 2-fold symmetry. Indeed, we can do that for a price. Rather than just having this one self-intersection line where 2 surfaces go through one another, we can have multiple of these bulges and all let them intersect on the z-axis. Okay? So I get much higher order self-intersection line with many more of these kind of clusters of Whitney umbrellas all placed in the same place, But now we get at least fourfold symmetry in this image. And having n equals 60, we could make essentially, say, 15 of these kind of crossing, cross-cap-like structures, and then have 4 of the color stripes on each one of them. Okay, we're done with just genus 1, the projected plane. So now we need to step up, still a long way to go. How about genus 2? How about genus 3? Tough luck. There are no regular surfaces on any of these beautiful objects. Not on genus 2, as I mentioned before, not on genus 3. So we really only have to start working at genus 4. And a few years ago, Marston Condor also published a complete list of all the non-orientable regular maps that exist. And there are far fewer of those. Okay? So it starts at genus 4, there are only 2 of those maps. Then there are 4 of genus 5, 3 of genus 6, 2 of genus 7, 1 of genus 8, and then 2 and 3 more on the next one and so on. But if you can find an example for all of these, I think that'll be enough for today. Okay, now I do basically pretty much the same thing as I did for the oriental surfaces. I find the right kind of body, and then I try to place the vertices in logical places, as much symmetry as possible, connect them up the right way, check the Berkeley polygons. So how do we make non-orientable surfaces of the right genus? Well, we start with a sphere, we take a hole punch, and every time we punch a hole, basically the Euler characteristic changes by 1. Okay? So we can get exactly the genus that we want by just punching enough holes. Then we have to close up those holes again. We could do it with disks, but that's kind of useless because that's just bringing us back where we started from. So instead, we plug up those holes either with these guys, okay, or with these guys, buoy cap or cross cap, and the first one you plug on there makes it single-sided. The next ones don't change anything like that. But every time we do that, we get the higher genus surface. We can also actually connect 2 of those holes with a handle. If we connect the holes on the same side with a handle, we might get a torus or something like that. That's not so good unless you use at least 1 of those in addition. Okay? But we can also use cross handles that start on one side of the surface, pass through the surface without making connections, come back from the inside. All of that is shown graphically here. So, hole punch, we go on genus 4, we punch 4 holes, we put 4 of these babies or these babies onto the holes, we have a nice genus 4 surface. Or, we can plug 2 of the holes with a handle, and then 2 more we can plug with 1 of these and 1 of those if you like. Or we can have these cross handles, or we can even use cross handles that in themselves essentially pass through one another. And then we can connect it to the same side of the surface, and we get the single-sidedness. And that's the trick that we're going to use. Now we need to figure out connectivity. Okay, that's what I did on the Poincaré disk, and then use the Coxeter relations. Fortunately, NSV has published on the web quite a few diagrams like that help a lot, so you don't have to do the tedious work for all of them, because some of them he actually published. And do these diagrams make sense? What's going on? So here we have this rectangle where we connect these 2 sides together, and we connect these 2 sides together, okay? And that basically makes a torus, okay? And then we add these little baseball kind of symbols, and that means we're taking one of these and plugging them here and there, okay? And each one of these changes the genus by 1. And so I can start with a torus and then add 2 of those, and that brings it, the Euler characteristic down to -2, and that's genus 4 that we want. Or we can start with this thing, which if you look at the H pattern actually forms a projective plane, which has genus 1. Then we add 3 more of those, which also makes it genus 4. Okay? So we have a variety of ways of actually looking at the connectivity. It's always the same regular map. Now we want to make 3-dimensional models. It's genus 4, so it seems natural to take a sphere and take 4 of those and put them down in tetrahedral fashion. Should make a very nice genus 4 surface. And you get something like that. Unfortunately, it does not work for the map 4.1. 4.1 in a way has a more tricky connection, but it works for 4.2. Okay? So symbolically, you see what we did. Here is essentially a paper model where each one of these caps is just shown by one of these rainbow discs. You unfold that thing, here you see the complete net. That would be the map 4.2. That would be the map 4.2D. The crucial thing about these little switching stations is they allow to essentially have multiple bands of color pass through one another and essentially reverse order without creating any crossings. And that's the nature of the projective plane that we essentially put there. You know, everything crosses through one another and switches order. Now, to make a really nice surface rather than this somewhat stiff model, I use a polyhedral approximation of that same geometry, and you can see I used 4 times the same geometry that essentially creates the 3 tunnels and arms here of a buoy surface. And then I use Catmull-Clark subdivision, which just takes all the faces, gradually subdivides them into smaller rectangles, and gradually smoothes out the dihedral angle. So you get these nice, smooth surfaces. There's an extra degree of freedom because we can put this buoy cap onto the tetrahedral faces with some rotational symmetry. Okay? And depending on how we place that, we don't change the genus. We still have oriented tetrahedral symmetry, but the transition between the different arms may be more or less pleasing, depending on what you like. So this shows 2 different rotations by 60 degrees of these buoy caps. I also showed you what happens if you go one more step of subdivision to make it nice and smooth. Now we need to go back to 4.1 where it didn't work. Okay? The problem is that it has face multiplicity 2, which means that each pair of faces borders to their neighbor not just once, but actually twice. So there are these clamps that kind of reach around. So a better match for this connectivity is a 4-sided prism with 2 perpendicular cross handles going through it. Okay? So 4-sided prism, 1 cross handle going through like that, 1 going through like that. If you unfold this, that's the net. This symbolically shows the entries to the cross handle, and that's what's going on the inside. Okay? You kind of see we have this ordering in the rainbow in one direction. We let this go through this internal pinch point. We get this ordering in the opposite direction. Okay? And it works not only for the map 4.1, it also maps for the dual. So once you have found a solution, the dual always maps nicely onto the very same structure, just exchanging vertices and face centers. All right, let's take an example from 5, genus 5. In this case, what's a good way of making this genus 5 surface that we need? We could plot 5 of those babies on this sphere. But you know, how do you do that? 1 north pole, 1 south pole, 3 around. Can we do better? Can we do more symmetrical? Well, remember, the Steiner surface is already of genus 1, has tetrahedral symmetry, has 4 bulges. Okay? So we plot one of these on each one of the 4 bulges of the Steiner surface. That makes it genus 5, and we still have tetrahedral surface symmetry. Isn't that great? So again, the rainbow disk essentially shows one of these buoy caps or cross caps plugged out. I prefer the buoy cap because I have 3-fold symmetry. We do that on all 4 bulges. We get from Steiner surface with genus 1 to something of genus 5. And it works beautifully. And again, here is sort of the unfolded map that is reminiscent of what we did for the hemicube, but now showing these 4 buoy caps and showing the color patterns. Again, you can see we exploit the fact we can go from blue through this thing to blue, and from red to red, and from green to green, without internally having any crossings or anything like that. That's the marvel of these tunnels and of the projected plane. This tetrahedral configuration is quite useful. It also works for N5.3, which is a self-dual map. Okay, so here a map is a map again where it and itself are looking exactly the same thing. And here I now show explicitly, if you take the Steiner surface, you put 4 of these on each of the bulges. Here I'm actually showing on the computer what this thing would look like and what the coloring would look like if you actually do that. All right, one more on 5.4. This one is pretty convoluted. It has face and vertex multiplicities of 3's. That means every face touches its neighbor 3 times in different places. Okay? And every n-gon basically goes back to one of the same vertex 3 times and then out of it again. Okay? So that's a pretty convoluted thing. And the tetrahedral symmetry just doesn't really work. Clearly a lot of symmetry of order 3 here. So what I do, I start with a torus, okay? And then we can put down essentially these buoy caps or cross caps, 3 of them somehow around the torus. But I think the nicest solution actually is to use the cross cap, okay? That's what I'm doing here. Torus, here's the cross cap, here's a cross cap, here's a cross cap. And doing that gives a very nice symmetrical 3-fold symmetric solution for this particular map. For map 6.2, I most conveniently use again cross handles, but this time we start with a cube, because this map has 6 decagonal faces, and it uses 3 cross handles going at right angles through the cube along the 3 main coordinate axes. The map also has 20 vertices. Okay? So it's very natural to put 8 vertices on the cube corners, 12 more on the center of the edges, and that actually works out very nicely. Here you see the virtual model. Here you see this thing unravel with the full coloring, showing the internal structure on the cross handles, and the folded up version on the right. All right, quickly, genus 7. Now we use a new trick. Genus 7. Okay, how do we do that? Again, we can say, how do we put 7 of those around the sphere? It's not going to be very symmetrical. But again, we start from a Steiner surface. We already get 1 genus for free. We need 6 more. Well, the tetrahedron has 6 edges. Okay, so let's plunk down one of these crossover thingies at each one of the edges of the tetrahedron. Unfortunately, in the Steiner surface, right on the edges that we have here, we have these Whitney umbrellas. Right? Kind of hard to plunk something like that down on a Whitney umbrella. But what we're going to do is we're going to take this baby, we cut off this thing here, right? So now it has the same kind of crease with sort of a figure 8 cross section, and we plunk this one down like that, so that the creases match. We basically fuse together these shallow figure 8 cross sections, one coming from inside out here on the Steiner surface, one coming from the cut off cross cap, and they nicely merge. So you make a nice smooth surface, and it has genus 7. Just what we need. And indeed, it gives a very nice rendering for N7.1 and 7.1 dual. You see the characteristic of this particular map. 7.1, and then the dual of it, and then here I fleshed out the surface and made it a little bit more smooth, so the creases are now sort of on the inside, you know, so the crease from here to there only starts about here and goes to the center. And to see that, let me again show a brief movie so you can really understand that structure. All right, that. And you can see 4 of the vertices are on the bulges of the Steiner surface. The other 6 are right here at the 6 half-axis of the coordinate system that essentially aligns with the creases. Here's another one right at that particular edge. Okay. So, I think a very nice solution for something of genus 7, tetrahedral symmetry. You wouldn't expect that that's really possible, but here it is. Okay. Okay. Now, genus 8, what we've been waiting for, right? Okay, let's wrap this up with a genus 8 sample. Since there's only one map, it's the only one. All right. How do we make genus 8? Well, that one is easy again. Okay, now we can use a sphere, now we can use our little thingies and plunk them down at the corner of an octahedron, and that should make a very, very nice surface. Okay? Now, this is a complicated map. It has 84 triangles, it has 36 valence 6 vertices, 126 edges, petri lengths of 9. I have struggled for quite a bit. I've not found the map, so sorry. Okay. Would have been nice to have a really, really nice map, but the surface itself is so nice that I just had to build it anyhow. Okay. I started again with a polyhedral model that is essentially one of these buoy cap structures. I slotted them all together, I did subdivision, and then I went one step further. I essentially made a grid, so the thing becomes somewhat transparent. To save time and material and money, I built this thing as two half shells. You see one half from the outside, you see the other half from the inside. And then I put both of these together. And in the back is the Golden Gate. This is just for reference, so you know the scale of this thing. And it was exhibited in Bridges last week, and you can see it from different angles. You can also come and look at it afterwards. So here is that genus 8 surface. Unfortunately, I do not yet know where to place the vertices and how to connect them. So still open problem, maybe. On the next symmetry convention, I'll have it. Some conclusions. There are many more maps that remain to be modeled, all the way up to, I think by now, Morrison contrast gone up to 200 in genus. But even among the first ones up to genus 8, there are several puzzles. And the big question is, can this thing be automated and programmed? I have struggled, Jack on Vig has struggled. We have not yet a program that does it. So let me conclude and say, can we turn some of this into art? And here's the basic idea. This is an oriental map of genus 3 made out of glass. Okay? I put 4 light bulbs into the corners of the tetrahedron, and then we're looking essentially at the light pattern that forms. So it's like a Tiffany lamp. Okay? Here is a more complicated example. It's an orientable genus 6 surface. And here's the light field generated by this particular Tiffany lamp. So I think these objects have indeed a lot of artistic potential. Thank you for your attention. Okay, now.
I was wondering whether there are what one then called isomorphisms between the surfaces and mathematical operations. Like in with matrices, you can talk about rotations that correspond to certain matrices. This looks a lot more complicated to do it, but I was wondering whether anyone has started to investigate mathematical relationships here. And the other thing is that there seems to be, there might be a kind of isomorphism between optics experiments. For example, in the projective plane, you have something going off to infinity and flipping upside down coming in. Well, if you have a lens, you can take an object and it moves in past a focal point and it flips upside down. So you might be able to generate surfaces by first starting with the optical experiment. I wonder whether...
So on the first question, yes, I think the mathematician actually have come from that way. And one of the earliest known regular maps, that black and white thing I had, 2.1, is the quaternion group. So the mathematicians are very much aware of groups of symmetry that come up in different contexts, out of matrices or out of rotations in space and whatever, and how they're related to those regular maps. Interpreting the regular maps as sort of actual surfaces on that particular handle body, to them, as I mentioned facetiously, it's less important because it's just a visualization, so there's nothing new in doing that. The thing about optics and projective planes, I haven't thought about that, but it seems promising. And of course, I teach computer graphics, the beginner's course. And very often they make a little sign mistake or something like that, and rather than projecting forward, they project backwards, and things kind of suddenly appear inside out, which is often very funny to see on a computer. So implicitly, I've certainly seen this happen, not voluntarily, by programming errors. Whether we can actually use it to make something constructive, we'll see.
That,
Let me take somebody else's
sorry.
question, Tom. Okay. Paul.
Is there, if you do the Van Wyk recursion but start with one of the nice versions, does that produce anything that's nicer than these pictures?
In Jack Van Wyk's program, you know, he starts from any regular map that he found. Very often these regular maps I see have very twisted edges. For instance, on the cube frames I have, almost every one of these modules, the edges wind around in a helical way around the arms. He then cubifies that. And that's now locked in. You know, he cannot change the geometry of that particular thing. And then he creates more twists on those twisted tubes already, and that gets locked in the next generation. So the higher you go, you get a more and more twisted tangles. And if there's a more regular structure, you know, it's not clear that he could ever find it that way.
No, but what you said was that even in some of the simple cases, he was coming up with quite nasty versions of them.
Yes, because they're generated from something even simpler that already had a little bit of twist, which is really not needed.
Sure, but if you were to start with the nice version rather than his nasty version, and just do the recursion once, would that produce something?
What do you mean by starting with the nice version?
Well, do the recursion process on the more symmetrical.
Oh, yeah, you would get something less twisted. Yeah, I mean, he could do that. He could take some of my hand models and do his approach, absolutely, and then find some of the same solutions he found, except they would be less twisted. Yes, definitely. Yeah.
So we had a discussion yesterday about symmetries of knots, and this idea of, given a knot, what is the most symmetric representation of that? So I guess that's an interesting question here to ask as well, is given a particular surface, is there a most symmetric way of representing that? So for example, these cross caps and boy surface all have the same genus, but
That's the focus of my work.
But they give a different symmetry.
That's, of course, exactly the focus of my work. And unfortunately, I have tried as hard as possible to find the most symmetrical solution. But in no case do I have really a proof that this is the most symmetrical solution, that somebody who's not clever could come up with even a nicer solution. Except Matthias Görner, a graduate student in mathematics who just finished his PhD this spring, he has been working in topology. And he's on the side, as a favor to me, kind of looked at some of these questions. And he gave me some limitations of what is possible and not possible. For instance, I tried very much to take the 7.1 map, which is of genus 7, and which I thought should go on an octahedral frame because it's so symmetrical. I just thought it's like Klein surface, only more complicated. It has 72 heptagons rather than 24. And I tried for 3 years to map this onto the octahedral frame. I couldn't find it, right? He finally did some analysis, and he said that the best you can expect is a D7 with 14 symmetry operations for that particular map. How he figured that one out is beyond me. It was very mathematical, very sophisticated, but at least it stopped me wasting time in a place where I couldn't find something. I then looked for something specifically of D7, and within a few days I found it. Okay? So there may be mathematics that can give you an upper bound of what is possible, and if you find a solution at that bound, then you don't have to search no further. But I think it's still open to really close all the holes here and finish that theory. So Matthias Görner is the guy who has worked on that and saved me maybe another year or two of my life. Okay, any more questions, Larry? No.
Well, I was, that, what is that fellow's name, Dijkstra? Or
Dijkstra.
Dijkstra, yeah. The mathematics can, there's a feedback, of course, between the two. He only looks at one side of the issue. Because if you have some mathematics, then you can see what the results are in a pattern, and perhaps vice versa, there's a connection between the two.
And he can see it without pictures, I cannot. He very proudly then said, none of my books has any pictures in it. And I said, that's why I never bought a book of yours. So, yes.
What surface we'll get when we'll join together three ends of cross handle?
Of what?
Of cross handle. You mentioned cross handles.
Okay, we can take 3 cross handles and you fuse them
Yeah, we have only one cross handle, and we join together. It's
into a loop.
yeah.
That's a Klein bottle.
Klein bottle.
Yeah. Okay.
just a comment, in physics, there's a treatise by Lagrange, I think it is, on analytical mechanics, and there's not a single diagram in it. But of course, later on, then you have things like Feynman diagrams in the context of variational mechanics.
Yeah, well, some
they
people
feed into each other.
Some people think more graphically, some people
Yeah.
think more formalistically. After that discussion with Dijkstra, I organized a panel discussion at CompCon called Pictures versus Parentheses. And it was the most stimulating discussion I had. They had to kick us out. The challenge came and said, go home now. No, we're closing at 9. It's 9:30, you know, and they're still questioning. Boy, people are really battling each other over that issue. Maybe you should have some coffee now.
If there are no more questions, let's give Carlo a Also, a reminder, the farewell dinner